All right, hello, future pharmacists. If you're studying for your B.Pharm, you already know that some of the biggest hurdles in medicine aren't just about the drug itself, it's about how you get it to the patient. So today, we are going to tackle one of the most fundamental formulation puzzles out there, the pharmaceutical suspension. Let's dive right in and uncover the science behind that little bottle. It all really boils down to this simple question. We've all seen that label, right? Shake well before using. It's on everything from antacids to kids' antibiotic syrups. And what that label is really telling you is that what's inside that bottle is in a constant battle with physics. Understanding why that is, and more importantly, how we can control it, well, that's the key to making medicines that are both safe and effective. So here's our game plan for today. We're going to start with the main challenge itself, then we'll dive deep into the microscopic forces happening at the surface of every single particle. After that, we'll look at the tools we have to get those forces under control, and finally, we'll put it all together into a kind of blueprint for designing the perfect suspension. Let's get to it. First things first, let's really define what we're up against. You see, making a suspension isn't as simple as just mixing some powder into a liquid. Nope. It's really about trying to defy physics. It's a nonstop struggle against the natural tendency of these little particles to just, well, misbehave. Okay, so here's the official textbook definition. But the part you really need to focus on is that particle size, greater than half a micrometer. Now, what that means is they're big enough to see with a microscope and, crucially, they are heavy enough to settle out over time. Our entire job as formulators is to manage that settling process. And this slide right here, this shows you the massive difference between success and failure. On the left, that's the dream. That's our goal. A product that gives a consistent, reliable dose every single time. But on the right, that's the absolute nightmare for any formulator. We're talking about a hard, solid brick of drug at the bottom of the bottle. And that's not just a product failure. It's a huge risk to the patient, who could end up getting way too little of their medicine or even way too much. So how do we stop that from happening? Well, the secret isn't in the liquid itself, and it's not in the solid particles either. It's at the invisible boundary where the two meet. We call this the interface, and trust me, it is the battleground where we either win or lose the fight for a stable suspension. Think about it like this. The surface of every single particle is buzzing with extra energy. It's unstable. It's kind of like it's uncomfortable being exposed to the liquid. So, to feel more stable and comfortable, the particles try to clump together. They aggregate. By doing that, they reduce the amount of their surface that's exposed. And this natural drive to clump together, that's the root cause of almost all our stability problems. Now, before we can even start thinking about how to stop them from clumping, we have to solve an even more basic problem. We have to make sure the liquid can actually touch the particles in the first place. And that brings us to our very first tool in the toolkit, wetting. So what is wetting? It's really just the process of kicking the air off the surface of a particle and replacing it with our liquid. If you fail at this first step, you're going to get ugly clumps of powder just floating on top of your liquid. You've lost the battle before it's even started, because a uniform dispersion is just impossible without good wetting. So how does this actually work? Well, imagine you add your drug powder to the liquid. Each particle is wearing a little jacket of air. Then you add something called a wetting agent. You've probably heard of things like polysorbates or sodium lauryl sulfate. This molecule is a game changer. It acts like a bridge or a peacemaker between the solid and the liquid, lowering the tension between them. This allows the liquid to spread out, push that air jacket off, and completely wrap itself around the particle. And just like that, you've got a wetted particle. Okay, so our particles are now properly wetted and they're dispersed in the liquid. Great. The next challenge is to stop them from immediately clumping right back together. And to do that, we can use one of the most powerful forces in nature, electrical charge. What's really cool is that when you put particles in a liquid, they naturally get an electrical charge on their surface. This charge then attracts oppositely charged ions that are floating around in the liquid, and they form something called an electrical double layer. So what's the result? Every single particle now has its own little electrostatic force field around it that repels all the other particles. It's basically built-in social distancing for particles. Now, to control this repulsion, we first need to be able to measure it. And that's where something called zeta potential comes in. It sounds kind of complex, but really, just think of it as the volume norm for repulsion. It's a number we can actually measure in the lab, and it tells us exactly how strong that repulsive force is. So if we can control the zeta potential, we can control the fate of our entire suspension. And this comparison is absolutely key. If you have a high zeta potential, you get strong repulsion. The particles stay separate, they keep their distance, and we call this a deflocculated system. But if that zeta potential is low, that repulsive force gets weak, and the particles can start to clump together or flocculate. Now, you're probably thinking, okay, high repulsion is always what we want, but it's actually not that simple. And this brings us to one of the most fascinating and honestly kind of counterintuitive ideas in all the formulation science. Sometimes, the best way to make a stable suspension is to actually encourage the particles to form loose clumps. It sounds wrong, I know, but it's a calculated risk. Look at the trade-off here, it's so important. The deflocculated system on the left, it looks great at first, right? The particles settle really slowly. But when they finally do settle, they pack together so tightly that they form that hard, concrete-like cake we want to avoid. Now look at the flocculated system. It settles much faster, sure, but it forms a light, fluffy sediment that breaks right back up with just a gentle shake. And that easy redispersion is exactly what we need. So here's the big takeaway. The goal is controlled flocculation. We intentionally lower the zeta potential just enough to let the particles form these loose, fluffy aggregates we call flocks. We're essentially sacrificing a slow settling rate in order to completely avoid the ultimate failure, which is caking. This idea is the secret behind so many of the best suspensions you'll find on the shelf. Okay, so let's put all the pieces together. Now that we understand these powerful interfacial forces, we can lay out a clear strategy, a blueprint, for designing a stable and effective suspension right from scratch. So besides managing all those forces at the interface, we've got some other physical tricks up our sleeve. For one, we can slow down settling just by making the particles smaller. We can also make the liquid thicker, more viscous, by adding things called suspending agents. This makes it a lot harder for the particles to fall. And finally, if we can, we try to match the density of our liquid to the density of the solid particles. These are all critical parts of a complete formulation strategy. So here it is, your final blueprint, the strategic toolkit for any suspension. Step 1. Use wetting agents to make sure the liquid actually coats the particles properly. Step 2. Control your particle size and use suspending agents to thicken the liquid and slow things down. And Step 3, the crucial final step, use flocculating agents to fine-tune that zeta potential, creating that perfect, easily redispersible sediment that prevents caking once and for all. So why is this so important for you right now in your studies? Because this knowledge is the difference between just following a recipe in your physical pharmaceutics lab and actually understanding why that recipe works. This lets you troubleshoot problems, it lets you innovate, and it lets you design products based on solid scientific principles, not just guessing and hoping for the best. And I'll just leave you with this one last thought. You are now armed with the fundamental principles that govern suspensions. But here's the thing. These unseen forces aren't just hiding in medicine bottles. They're at work in paints, in salad dressings, in inks, in so many products all around you. So the next time you pick up something that says, "Shake well," you'll know exactly why.